This short video represents the first part of Lesson 8, which is how charged particles move through electric fields. Okay, so this first part, this is part A, this represents the first segment. So we know what electric fields are, we've seen them. We've talked about the potential energy that's associated with them. And so now we can start to begin to talk about, hey, what does the motion of these charged particles look like? Let's start by doing a little thought experiment. Let's consider a small test charge. It has a tiny mass, so we're not going to worry about gravity. And we're going to place it in a vacuum. Here's a charge Q, which is creating an electric field. And QT is placed some distance r from this test charge. We know that there's going to be a force. We know that there's certainly energy that's associated with all this. And so let's kind of carry this through. From Coulomb's law, we know that this is what the force is. And so if this is what the force is, and it's the only force because we're not worrying about gravity, we can use Newton's law to say, hey, let's find the acceleration of what this particle looks like. Because perhaps we could use kinematics to describe its motion. And we say acceleration is equal to the electric force divided by the mass. We'd like to do this, but we're going to encounter a problem. And here it is. Here's my test charge, and here's the charge that's creating an electric field. If this is positive and this is positive, which we may as well assume that they are, we know that the force is, of course, proportional to this distance. And it's going to want to repel. Well, as soon as it repels a little bit, well, now its distance has changed, which means the force has changed. And again, if it moves even more, well, now it's moved to this distance, the force has changed again because the distance has changed again. And what we notice is if we look at the acceleration then, if my force keeps on changing, then that means my acceleration keeps on changing. And that's a major problem. Because if you'll recall, when we derived all of our kinematics equations, we made one assumption. For all of those kinematics equations, we said that the acceleration has to be uniform. It's got to be the same. Our acceleration can't be changing. And so all the equations that we used for kinematics then are useless. And so we say, okay, so we can't even consider force when we're talking about charges moving through these types of electric fields. Okay? We need to look somewhere else. And so we're going to look at energy, because energy doesn't care about accelerating uniform or non-uniform acceleration. Energy doesn't care about that at all. And that's one of the reasons why energy is such a valuable tool. As the test charge and the charge that's creating the field separate, the electric potential energy decreases, and the test charge, of course, gains kinetic energy. And so the conservation of energy tells us that the decrease in potential energy must equal the increase in kinetic energy. So here's what that looks like, okay? This right here is the conservation of energy. Energy initial equals energy final. It's just written in a slightly different way. And if you really, really want to, we could take this, and maybe ask me in class tomorrow, we could take this and I could prove to you that this equation right here means the same thing as energy initial equals energy final. It's just I'm putting all the potential terms on one side and I'm putting all the kinetic terms on the other side. Okay? So let's continue our discussion. For 2-point charges, this is what we get. Here is, of course, the electric potential energy, and here's kinetic energy. So we have K, QT, the test charge, times Q, the charge that creates the field, over this separation, the second separation, minus K, QT, Q over R1, the initial separation. This is, again, the change in potential energy. This is, of course, equal to 1/2 mv2 squared minus 1/2 mv1 squared. That's it. now that we kind of have said, oh, that's kind of what we're looking at, we can do a whole bunch of stuff with that. So here's a small pith ball. It's got a mass of 1.0 times 10 to the minus 5 kilograms. And it's got this charge, 2.0 times 10 to the minus 9 coulombs, and it's at rest, 25 centimeters away from a fixed charge of 5.0 times 10 to the negative 6 coulombs. We're going to neglect gravitational effects. We're going to neglect air resistance. How fast will the pith ball be moving when it's 50 centimeters from the other charge? So it's going to go from 25 to 50, and we want to figure out, hey, what speed does it have when it's at 50? Okay, so here's what we know. These are all the things that we know. We also know a little bit about the charge that's creating the field, right? And we know about the initial and the final separations. So basically, this is our situation. This guy's fixed in place. He creates a field. This guy is going to zoom away from him because they're both positive charges. They're going to repel. And we start off with our conservation of energy. And we say, hey, the potential energy, the difference in potential energy that this guy experiences is going to be transferred into kinetic energy. And so, again, this is almost directly what we wrote right above. We just say, oh, okay, well, delta EE, here it is, E2 minus E1 equals EK2 minus EK1. Now it starts at rest, so there is no initial kinetic energy. It just starts at rest. And from here, we can just sub in what our numbers are. Now, there's a lot of numbers to sub in, but we certainly can do it. And so this is what we've done. Subbed in all these numbers, and you'll notice no variables here, no variables here. M, we know what it is. The only variable is V2. And so when I punch this all into my calculator, I multiply by 2, I divide by M, I take the square root, everything's all said and done, I get 6 meters per second. And so if you want practice doing this, I would invite you to try this, but you will get 6 meters per second. And it's like, oh, I didn't even need to use Newton's law because I can use energy to do this, okay? This is very, very standard example for how, when we have a point particle, we can calculate the speed of a test charge moving through this electric field. And that is part A of this lesson.